I am super excited because if there's one industry that is going through a lot of transformation right now, it is automotive. At least I think so. And I am really excited to see what you're going to tell us about the software and electrical architecture platform.
Okay.
Thank you very much.
Thank you for the invitation. So apparently I'm a dinosaur. And I represent an industry that is, as Jan said, going through a tremendous transformation. But what we're going for is catching up with the rest of the world. Now that we are beginning to catch up, it seems like the rest of the world is moving on. So, yeah, funny how that works. Okay, so I will be talking about some architectural principles that we defined for the next generation of our EE platform, EE and software platform. Let's see if this works. Yeah, so Volvo started almost 100 years ago. Next year we have our 100th anniversary. So from 99 years ago, we have this OV4, the first mass-produced Volvo. And the newest one is the EX60. Software content here. The first one, of course, nothing. The second one, lots and lots. I don't know how much in lines of code, but there is a lot of software. And that's really at the heart of where we're going. We're going for, and this is the current buzzword in the industry, software-defined vehicles. What does that really mean? Well, no one is really sure what that means. There is no good definition of software-defined vehicles. However, it's not just a lot of software. Cars and vehicles have had a lot of software for decades already. We're in hundreds of millions of lines of code. So it's not about the contents or the size of the content. It's something else. Let's see what that is. The best analogy that I have found is in mobile phones. The old phones from the 90s and the aughts, like the Nokia and the Ericssons and the Sonys, there's software enabled. There is lots of software in there, quite advanced software, but it doesn't really change over time. And the product is static. From 2007 and on, you have a different kind of phone, which is more software defined. And the software kind of defines what the product is. And that's really at the heart of being a software-defined vehicle as well. So what does this mean for a vehicle? Well, from a customer perspective, it means that your product will improve over time. The old cars, they are at its best when you buy it, when you drive out of the lot. Nowadays, they will get better over time. So it's actually at its worst, hopefully, when you drive it out of the lot. You will get over time improved vehicle dynamics functions, maybe better traction control. The driving just feels better over time. Driver assistance, the ADAS systems improve over time. Infotainment gets better. Like Volvo is running out Gemini over our fleet as well. Something that people who bought the car 2-3 years ago, they didn't even know that Gemini existed. And now they get it in the car. Electromobility, of course, will improve. And one thing that car industry has been extremely bad at is getting new features out into existing cars. And that's something that being software defined would actually allow us to do. But enough about the customers. What about the OEMs or the vehicle manufacturers? What do we get from this? Well, classically, OEMs have not really been software developers. They have been system integrators. We buy all our stuff from suppliers around the world. We build it together, and we hope that it works. With this move, we can actually take more of the software development in-house, and all the stuff that is important to kind of provide a customer experience is something that we can control ourselves. With that, we can also increase innovation speed. We can democratize the access to sensor data and to actuators. The classical approach is you have a lot of functional silos, and if you're in this functional silo, you don't really care about all the others. So if we open this up, we can use, for example, the cameras that are used for ADAS system. Those camera streams can be used for other functions that have nothing to do with ADAS. Increased virtual verification of target software. we can verify the hell out of it before it even sees a vehicle. Current verification approaches almost always require that you build vehicles to actually test these things. So we can constantly improve quality, and we also get adaptable products. So laws change, regulations change, customer wish and customer sentiments change, and we can change the product with that. Previously, that was difficult. So that's the software-defined vehicle. How do we build a platform that kind of caters to these things that we want to achieve? So what we've done then is we look at the principles, or some principles that have been defined for software architecture, software systems, and see, can we apply those at the system architecture level? What does that mean? And here we go for the solid principles. What if we were to apply these to the overall EE architecture? Solid, and most of you maybe know these already. So this is fairly high level, simplified view of these principles. The S stands for single responsibility principle. So basically a module should have one and only one reason to change. Essentially, this is about cohesion, right? A module, everything in a module should somehow belong together. If you have stuff that doesn't belong together, you have lower cohesion, and you have multiple reasons for changing that module. So that's what you want to avoid. O stands for open-close principle. Basically means that a module should be open for extension, but closed for modification. So what does that mean? Well, it means if you want to add functionality to a module, it should be done in such a way that what is already there doesn't need to change. That is unchanged. It is compatible backwards. It's, you don't change those things. Typically, this requires that you have well-defined and stable interfaces, and you have a good evolution of those interfaces. L stands for Liskov substitution principle, and this, because it has a Russian name in it, is the most scientific one of these principles. It says that subtypes must be substitutable for the base types without altering correctness. I'm not fully sure myself what that really means, but basically it says that a module that implements an interface, it needs to adhere to both the syntax and the semantics. So if you exchange a module for another module, as long as it has exactly the same behavior at the interface level, it should be interchangeable. The users of those interfaces, they should not see a difference. I stands for interface segregation principle. So basically, no client should be forced to depend on interfaces it does not use. So what does that mean? Well, basically, you should split your interfaces into good chunks, also in a cohesion way, if you will. No broad monolithic interfaces. And this is essentially about managing coupling, the dependencies between your modules. The last one, D, stands for dependency inversion principle. And essentially, this is high-level modules should not depend on low-level modules, and both should depend on abstractions. So basically, if you have a software stack, every higher level layer that uses the API of the lower layer automatically gets a dependency to the lower layers. So the way to do that, or to break that dependency, to turn it around, is to define an abstraction that you put in between. The higher layer defines that abstraction, and the lower layer kind of has to adhere to that abstraction and make sure that it fulfills whatever that abstraction is set to fulfill. This is not just a translation, it's actually more of a contract thing. So this is, at a glance, the set of solid principles. What do these mean from a software and EE architecture perspective then? Well, the S means basically that all our modules should be defined based on some kind of separation of concerns. So we have functionality, going for cohesion, different functional domains in the vehicle. They should all be, they should not be conflated. You should look at the change rate, the cadence. Some things in the vehicle we want to change faster than others. Do not mix that cadence. Real-time needs. Some are really hard real-time systems and some are softer. Do not mix those two. ASIL, or the safety integrity level, don't mix those either. So it's essentially about isolation between modules to create this independence. The O means, okay, we need stable module interfaces so that we can have this substitutability, and we want to abstract module implementations. So working with interfaces is kind of key here. New functionality should be added as new modules without an impact on existing modules. For the L, we need to ensure interchangeable modules and make sure that they are interchangeable by having some kind of conformance testing. That's saying, okay, the old module works like this, the new module actually fulfills all the same conformance tests as the old module. Then we can replace it. We are pretty sure that it works. Interface segregation principle is basically publish the interfaces that you use, don't publish everything you could. Be mindful of what the interfaces are that you actually expose. Just exposing everything is actually not a good thing. Only expose the things that are actually needed. And don't have monolithic APIs. Split your interfaces into reasonable chunks, and that makes sense. And from a D perspective then, and this is maybe, at least to me, one of the most important ones, high-level policies must not depend on low-level hardware, because the mechatronics of a car, they will change over time. The high-level customer functions should not have to change just because you do a sensor switch or an actuator switch. So, but in order to kind of dive into the details of how solid can be used in an architecture perspective, we need to redefine what a module means. In the classical original setup of the solid principles, a module is a class. This comes from object-oriented programming. So a class defines an abstraction of something. It provides an encapsulation, and it exposes an interface for that interaction. So in order to apply all these solid principles to a larger context that we're working in, we need to redefine what this module is, because it's not a class that we're talking about. So instead, we kind of define some kind of execution unit, if you will. Some kind of module, some kind of building brick. And what we need to ensure is isolation in many different dimensions. One is temporal isolation. So the execution time allotted to one execution unit cannot be used by other execution units. So you're sure to get the time that you need. Spatial isolation. This is nothing related to COVID. So this is more, don't touch my memory and I won't touch your memory, basically. Resource isolation. And this is dealing with IOs and the low-level hardware of the system. Different execution units should not share IOs, for example. And when you share hardware, make sure that you share it in a responsible way, and hopefully don't share it. So typical mechanisms to get temporal isolation, for example, is hypervisors, microkernel operating systems, RTOSes, where you have these execution units that are separated from each other. Spatial isolation is basically memory protection. You need some MMU or MPU in there. And IO-MMU for the resource isolation. Typical communication mechanism separation is VLANs on Ethernet or time-aware shaper to kind of make sure that the traffic flows are separated from each other. So let's dive into some more details. What does this mean? Because now we're getting into what are the principles that we're setting up. Well, the S is basically we have to modularize our software. And here we modularize both in verticals, the functional aspects of it, and in horizontals, which are more dependent on real-time aspects or where in the software stack we live. We'll go more into details in just a couple of minutes. And also modularization of hardware. So different execution environments that are suited to host different kinds of software. So we could have, for example, high performance, soft real-time, QM. QM basically means there are no major safety implications if something goes wrong. Typically infotainment systems and more user-facing stuff like climate and things like that. We can have high performance, soft real-time, but up to ASIL B. Now we're climbing up the safety ladder up to if something goes wrong, it's not good, but you can handle it. We have acceleration, soft real-time. We're starting to get software into the vehicles that actually don't really run that well on a classic CPU. You need acceleration hardware. Typically ADAS functionality for image recognition and stuff like that. We can have low power soft real time, so stuff that runs while the rest of the vehicle is off. Power efficient, hard real time, like some actuators actually need hard real time. Power efficient, hard real time up to ASIL D. ASIL D is the highest level. If something goes wrong, you're in deep shit, basically. So it should not happen. So you need hardware environments that can host all these different kinds of functionalities. You cannot mix them because currently there is no hardware that can run all of this. And basically you also want to separate the mechatronic systems and controlling those from the higher level functionalities. So the O and the I we can actually combine a little bit. This is basically all to do with interfaces. So what we need is we need to have well-defined and well-governed interfaces. And that's something that traditionally the automotive industry is not super great at, managing the interfaces of the building bricks inside the vehicle. That's why it takes so much time to build vehicles. So essentially you need to, again, separate the low-level mechatronic control from the high-level customer features, if you will, and make sure that you have a well-defined interface between these two. And again, we need to have these narrow interfaces, not one big interface that covers everything, but actually smaller chunks of the interfaces that can evolve individually. And also when we communicate data over these interfaces, make sure that we don't mix data from different signals, different services from different interfaces in the same packets on Ethernet or on CAN. For L, this is basically, the main use for this is when we deal with supplier systems. If we want to have dual source, for example, being able to buy the same component essentially from two different suppliers. Everything that we just said about interfaces applies here too, but we also need to be sure that we have really great conformance tests so that we can make sure that whatever supplier A provides and fulfills the conformance tests, supplier B also passes these conformance tests. Then we know that we can actually exchange these two. And we need to separate OEM concerns from supplier concerns. Suppliers are experts in, for example, steering systems, braking systems, whatever mechatronic systems, but they're not always that great at building the complete vehicle. That's what the OEM is there for. OEMs are not always experts in braking systems and steering systems, but we know how we want to combine these things to create the customer experience. So we need to separate those concerns. D then, dependency inversion principle, is basically, again, separation of policies and mechanisms. This comes back again and again, so it's really a key principle. We need to define some kind of hardware abstraction layer. So something that abstracts the fundamental mechatronics of the vehicle from the higher level vehicle control parts. And we need to have some kind of interface as well that separates the fundamental vehicle, the base vehicle, if you will, from the higher level customer features. And the base vehicle is basically a vehicle that you can drive, brake, and steer, nothing else. And this leads us to a list of architectural principles that we've used to define the platform for the EX60 and the vehicles to come. So in the system and software structure area, we've said, okay, we need a layered system architecture. We have core compute, zonal control, and a mechatronic rim where we have all the mechatronic stuff at the outer rim. A layered software architecture, we need to define modules by function, change rate, ASIL, real-time, so on. Interfaces, an extremely important part. Abstraction of mechatronic systems and capabilities, stable and versioned interfaces, full semantic interface contracts. So not just the syntax, the semantics, and we actually need to start working with these contracts as well. Narrow, purpose-specific interfaces, and abstraction of underlying compute platform. So no bare metal stuff. We actually have an abstraction underneath that extracts the specifics of the hardware. And isolation becomes a really important principle here as well. Isolation of modules in the core computers, for example, using hypervisors or microkernels and microkernels. Isolation of modules in the zone controllers. They're running classic AutoSAR, so we need to use AutoSAR partitioning there. Use core affinity and static priority scheduling for real-time applications. Allocate I/O to just one module, and that module will then arbitrate multiple requests for that I/O. We need to isolate communication as well, using VLANs on Ethernet, for example, and isolate on CAN by using individual things per mechatronic system. So let's see how this kind of impacts the system. So the software stack, and this is not really rocket science, all software stacks look like this. So you should recognize this as well. At the foundation, we have the operating system. On top of that, we have a middleware, some kind of glue that provides the distributed platform. And on top of that, we have our applications, the payload of the system, if you will. And the cadence of growth, of course, increases as you go up. Operating systems should not really change that often. And the feature growth should not be that great either. Middleware, they can change a bit more often depending on the needs from the applications on top, but they should not change as much either. It should be fairly stable, depending on which part of the system you are in. The applications, on the other hand, that's where we want to see the change. And maybe not all applications, but some applications need to change fairly often. So let's open the application box a little, because there we have a layering as well. At the very bottom, we have mechatronic control. The software, the applications that control the mechatronic systems. These should not change very often. These should basically only change if you find a bug or you change something in the mechatronics of the system. Vehicle control is the next layer, kind of coordinate some mechatronic systems to drive the vehicle. They should not change that often either, but they might change a little bit more often than the mechatronic control. And on top, you have the vehicle management part, which is really the high level, let's call it the fluffy functionality, if you will, or the stuff that brings you joy as a user. Just being able to steer the car might be good, but it doesn't really give you joy. So here, we want to have the ability to change that functionality quite often. If we look at some aspects here, real-time aspects, hardest in the middle, in the bottom. Mechatronics control, often hard real-time. Vehicle management, at most soft real-time, often no real-time at all. Safety, of course, high safety levels at mechatronic control. At the top, not so much. Hardware dependency, mechatronic control, yeah, lots of hardware dependency. At the top, hopefully none. Interface stability at the bottom, well, depending on how much the hardware changes, but the interfaces here should be fairly stable because nothing really changes in the steering system or the braking system or the climate control system or whatever. At the very top, we can change these interfaces as we want to add more functionality. So if we plot this into a matrix, we have the software stack as the y-axis and the application layers as the x-axis. And all these cells, we can kind of plot some kind of update cadence. And the highest speeds are, of course, in the top right corner. So vehicle management, which is top-level functionality, a little bit in the vehicle control, and the middleware should be stable, but could change for vehicle management requirements if there is something that trickles down. And this is really the part that should be software defined. So it's not the entire vehicle that should be software defined. All the safety stuff, the real-time stuff, all of that should be stable. So how does this then, how do we use all these principles when we define our platform? If you open up an EX60, this is basically what you see. You have a core compute cluster consisting of two main computers. They are the UXC, or the user experience computer, and the VCU, the vehicle control unit. These are our high-performance computers. At the next layer, we have a bunch of zone controllers, one for the right side and one for the left side, and a little junior zone controller, if you will, an I/O controller in the back of the car. And around that, we have a number of more specific mechatronic systems like brakes and steering and the airbag. So the VCU hosts a lot of applications related to high-level functionality. In the UXC, we have, of course, infotainment functionality. We have our Android stack. Zone controllers, they integrate most or many, at least, sensors and actuators for a specific zone, the right side and the left side. And here we also have hard real-time and ASIL. The TCAM is basically our connection point to the outside world, wireless connection point. Yeah, I/O controller is essentially a junior zone controller, as I mentioned. So how does this then fit into there? If we recall this matrix, if you will, the high-level parts, they go into the core computers. So the infotainment computer and the vehicle computer. The low-level parts, they go into the zones and the mechatronics. So here we have, from the principles list, a layered system architecture with a core compute, zonal control, and mechatronic RIM. We have a layered software architecture, and we are defining modules by function, change rate, ASIL, and real-time. There are some other factors as well, but those are the main ones. If we go into these principles then, mainly interfaces and separation, recall the application stack that we have on the left side of this picture. We'll come back to that. But we have network isolation on CAN. So each mechatronic system in the mechatronic RIM actually has its own CAN link. Traditional systems, you have many different systems on the same CAN link, so they share that shared resource. Here we have said, okay, one system, one link. Good isolation. We have network isolation on Ethernet using VLANs. So it's basically dividing the Ethernet pipe into multiple virtual pipes. And you cannot cross the streams, so to speak. We do abstraction of mechatronic systems and capabilities, and we allocate I/O to one module and one module only. And then we arbitrate multiple requests to those I/Os. And what does that look like in the software? Well, the mechatronic control is in the mechatronic RIM and in the zone controllers. But what they do is they provide us with an interface to those mechatronic capabilities that hides away all the nitty-gritty details of the mechatronics. We actually have mechatronic control also in the core computer because some of the sensors are directly connected, like the cameras, for example. So we need mechatronic control also in the core computer. On top of that, we have our vehicle control. So actually the functionality that lets us steer the vehicle and accelerate, decelerate, all those things. And again, we define an interface to those capabilities that then can be used by high-level functionalities. So we have stable and versioned interfaces, full semantic interface contracts, and narrow purpose-specific interfaces, and essentially two interface layers, if you will. A hardware abstraction layer that provides this abstraction of the mechatronic parts, and the vehicle service layer that provides us with, this is how you steer the vehicle. And on top of that, we have our top-level functionality. So the last set of principles here then, abstraction of the underlying compute platform and isolation. How do we do that? Well, these are the high-level software stacks that we have in our computers. We have in the vehicle control computer, that high-performance computer, we have an NVIDIA SoC running NVIDIA's hypervisor. On top of that, we use QNX. And on top of that, we have our own middleware, the core system platform, that essentially abstracts away all the nitty-gritty details of the underlying platform. So the applications, they don't really know that they're running on an NVIDIA platform. They just know that they're running in a Volvo environment. So we could essentially change the underlying hardware if we wanted to. And we're actually running the same application software on x86 for testing in our labs as we do on ARM. That is the fundamentals for the NVIDIA SoC. And all that is handled by the core platform. Sorry, let's go back. In the infotainment computer, we're running a Qualcomm SoC, also using QNX as the base operating system and as a hypervisor. So we have hypervisors here in the core computers. We're also running microkernels. QNX is a microkernel, not always running virtual machines, but we have fairly good separation between the processes in a microkernel. In our Linux systems, we're using C groups for isolation. Linux does not do safety, so we don't have any ASIL requirements on Linux today. It might do it in the future. And we have this abstraction of the underlying compute platform, which is also one of the principles that we had. So, with that, concluding, Solid is not just for code, it actually scales to system architecture. Turns out that those principles are quite universal. So from an architecture perspective, this is actually a good set of principles to follow. Some highlights. If you solidify your software-EE architecture, you get modules defined based on function, change rate, real time, that kind of thing, separation of concerns. Separation between modules is key. You need to be able to separate in space, in time, and with resources. And really, interfaces become extremely important. Manage and define those interfaces as though they were gold. And looking at the software content of an EX60, I looked a couple of weeks ago. The complete binary is just over 5 GB. I'm not sure what that translates to in lines of code, but 5 GB is where we're at this point. Now, if you follow all of these things, what you get is you actually reach the top level of a ranking of SDVs in the world. And Volvo is currently the only traditional automaker that reaches level 5 on this scale. Interestingly enough, Tesla is not on level 5. So, that's about it. Thank you for your attention.
Wonderful. Thank you very much, Martin.